everybody. Here's the path that a point on the perimeter of a rolling ball takes as the ball rolls without slipping. We talked last week about the idea that a complicated path can be described if you add together vectors that are each doing one simple thing. So here we have a vector that's just getting longer, and we have a vector that's just rotating. And when you add them together, you get this nice rolling ball path. Here's the same image, but still. And we thought, okay, let's have a vector that points straight up so that the center of the ball starts at 0, 2.5. Then let's have a vector that stretches horizontally and a vector that rotates. And because vector addition adds vectors from end to end, you're going to get that nice path. So this was what a lot of groups did. They said, okay, 0, 2.5 is the upward vector. Let's have a vector that points right but gets longer with time because we're scaling it. And then let's have a rotating vector whose length is the same as the radius, because otherwise the vector wouldn't extend all the way to the edge of the circle that we want to model the rotation of. The problem is that this very sensible set of equations doesn't produce this nice path, it produces this path. Let's see what this one looks like when it's animated. So clearly the path is wrong, but I asked the groups earlier today to notice a couple of specific things that are leading the path to be the incorrect shape. A lot of groups noticed that the rotating vector is rotating in the wrong direction for a rolling ball. It should be rotating clockwise. A couple of groups also noticed that there's a problem with the very starting. Here at time equals 0, you can see the purple vector is at an angle of 0 because it's facing right. But if you look at the path we want, the path starts from the top of the ball, so the rotating vector has to be facing up at an angle of pi over 2 when time equals 0. So let's fix those couple of things. The groups noted that you don't need to change this vector or this vector, because everything that's going wrong is about the rotation that's happening, and this is the only vector that affects the rotation. So let's rewrite it. If we want to fix the direction of rotation first, instead of having the angle go up with time, we can have the angle be the opposite of time. This sort of makes sense if you imagine angles. So let's say this is an angle of like 10 degrees. Negative 10 degrees would be the same angle but in the opposite direction. So when I have positive t here, as t goes up, the angles are also going up in that direction, which would be a rotation that's counterclockwise. Here, when I have the negative sign, when time goes up, all the angles are going to be the same numbers but negative, and so that means that the angles will go the other direction, and so we'll rotate clockwise, which is the way that we want. The problem is, at time equals 0, the angle still isn't pointed straight up and down, and you can see that if you imagine plugging in time equals 0. If you plug in 0 for t, that whole number becomes negative 0, but that's still just 0. And so you'll be taking the cosine of 0, where that's the angle. So we haven't actually managed to change the starting angle. So right now at time 0, the angle is 0, but I want it to be pi over 2. So let's just add pi over 2. Now, if I plug in 0 for time, I'll have pi over 2 minus 0. So that gives me pi over 2. So you can think about that sort of like the starting angle. Great, so now we've fixed those two problems. It's going to rotate in the correct direction, and the starting angle is also correct. Let's see what it looks like now. Now it looks like this, and you can see that the rotation is happening in the right direction, and the start of the path definitely starts at 5, so the starting angle is correct. But we still have these loops, and if you think about what's happening, it looks like the rotation is faster than how far it's translating over. So it's almost as if like the wheel is slipping on ice or something. So there's two more things that we have to fix. We have to match the horizontal speed with the rotational speed so that the ball will roll without slipping. And there's one key fact that lots of groups discovered, and some groups I nudged into discovering, that helps you match those speeds. Here's the idea. This is a radius 1 ball that's rolled for 1 revolution. This is a radius 3 ball that has rolled for 1 revolution. How far did each one actually roll? What was this horizontal distance? So if you think about how far that must be, the entire perimeter of the ball has to roll before the upward angle can become upward again. So I'm rolling around 1 full perimeter's worth. What's the length of the perimeter? That's just the circumference, which is calculated as 2 pi times the radius. So since this radius is 1, the circumference here is 2 pi. Here the radius is 3, so the circumference would be 2 pi times 3, or 6 pi. Okay, so keep this idea in mind, because it's going to be really key to figuring out both how fast should it be going horizontally and how fast should it be rotating. Come back in the next video and we'll think through how you can use these facts to set up solutions to your problems.